and welcome to the Spring 2008 Cyberseminar series with Jim Smith from Princeton University as today's speaker. At this time, all participants are in a listen-only mode. We will be facilitating a question and answer session towards the end of today's conference. If at any time during the call you require assistance, please press star followed by 0, and a coordinator will be happy to assist you. I would now like to turn the presentation over to your host for today's conference, Mr. Conrad Madiak, Communications Manager for SCUAHSI. Please proceed, sir.
Thank you, Grace Ann. Good afternoon, everybody. I'd like to welcome you all to this third in the series of 4 spring cyber seminars that SCUAHSI has set up. If there's anybody on the line or on the visual part of this web conference that hasn't dialed in, we have dial-in instructions that were in the email, or if you need that, just put a note in the chat box, send it to the host, and I'll get you that information. I'd like to do just a brief introductory comment about Jim, but let me first run through the beginning first series of slides here. That as we mentioned, that Jim Smith from Princeton University in the Civil and Environmental Engineering Department is going to be doing a presentation on flash flooding in the urban environment, lessons from the Baltimore ecosystem study. David Kirchtel is not with us today. He's out traveling, but if you have any questions about the technology or any questions about dialing in, as I mentioned, just send a chat message to the host, and I'll get back to you. We'll, later on, once we have the recording of this and a PDF version of these slides, they can be downloaded probably early next week at SCUAHSI.org at our website, sem-current.html, on that particular page. We also have and the last in the series for the spring, on April 25th, we're going to be having another cyber seminar on Hydro NextRad with Witold Krajewski, the NextRad, the community resource for the use of radar rainfall data. I'd also like to remind anybody who hasn't already received an email from the communications manager about the SCUAHSI Science, the biennial science meeting, which is being held in Boulder, Colorado, July 14th through 16th. There's more information on the SCUAHSI website about that. And also a reminder that we are sponsoring a hydrographics visualization competition. Information is also available on the SCUAHSI website about that interesting competition. But in preface to Jim's presentation, I just want to read a little bit about Jim. That Jim Smith's research interests concern the hydrology, hydraulics, and hydrometeorology of extreme floods. His hydrometeorological studies have centered on the development of technologies for measuring rainfall from weather radar, stochastic modeling of the space-time structure of rainfall, and microphysical studies of extreme rainfall from organized systems of thunderstorms. Jim's research group has been involved in numerous hydrometeorological field campaigns, most recently in connection with the Baltimore ecosystem study, a component of the NSF LTER program. Field studies in the BES have also examined the heterogeneity of hydrologic response in urbanizing watersheds, the stability of the channel floodplain system in urban drainage networks, and the hydraulics of extreme floods in urban rivers. And his presentation today will be drawn from this work. So without any further introduction on my part, I'd like to turn the presentation over to Jim, and I'll be giving him control of the slideshow. And just sit back and enjoy. And as Grace Ann mentioned, there will be a question and answer period at the end of the presentation, so look forward to your questions. Jim, take it away.
Okay, thanks very much, Conrad. So I will be talking about flash flooding in the urban environment centered on the Baltimore metropolitan region. The Baltimore metropolitan region in part because of the resources associated with the Baltimore ecosystem study, as Conrad mentioned. As we'll see, the Baltimore metropolitan region is an interesting area to look at flood response in urban settings because of this rich set of resources. It is a setting that is typical of flood response throughout the eastern United States, from Charlotte to Boston, Massachusetts, and it broadly reflects themes that center on flooding in urban environments. So the work will be specific to the Baltimore metropolitan region that I report, but it's going to have broad implications for flooding in urban environments throughout the United States and around the world. What I'd like to focus on are four broad areas dealing with flood response. Two related themes are going to be hydrology and hydrometeorology of flooding in urban environments. And in examining the hydrology, the focus will be on some of the specific elements associated with the urban environment, looking at runoff production in terms of alterations of the land surface associated with impervious surfaces, alterations of soils, and in particular the role of urban soils, and then stormwater management as it plays into runoff production in urban areas. A central theme that I'm going to examine today is the role of warm season thunderstorm systems for flood hazards in Baltimore and again more broadly throughout the eastern United States. So understanding the variability of rainfall in space and time, and also examining how the urban environment may alter the behavior of warm season thunderstorms is an important setting. We'll also point to the fact that in the eastern United States, our urban corridor has characteristic features associated with mountain regions, the Appalachians to the west, and land water boundaries to the east that play an important role in looking at flood hazards. The second collection of themes revolve around the hydraulics and geomorphology of extreme floods in urban environments. And looking at the hydraulics, we're principally concerned here with how urban infrastructure is going to alter the response of flood waves as they pass through the channel floodplain system, how they ultimately alter the channel floodplain system, and this alteration is going to be an important part of the geomorphological issues we look at, in addition to one of the most profound alterations, and that's associated with burial of the headwater channel system and replacement with a very dense network of storm drains. So these are going to be the themes. The area shown in the image here is the Baltimore metropolitan region. The purple line divides Baltimore City on the inside and Baltimore County on the outside. The highlighted watershed that flows from Baltimore County into Baltimore City is the Gwynns Falls, and it's the principal study watershed of the Baltimore ecosystem study. I'll be examining Dead Run, which is on the western margin of Baltimore City extensively, and then Moore's Run, which is in the northeast corner of Baltimore City. But to begin, I want to illustrate some of the things that happen when we make the transition from forested landscapes in this region to urban. In the Baltimore ecosystem study, Baseman Run, which you see in the very northern portion of the image, is the forest reference watershed for the Baltimore ecosystem study. White Marsh Run, which is just located on the northeast corner of Baltimore City, particularly the headwaters, is a dense urban watershed, or a densely urbanized watershed in Baltimore County. And in this figure you see the contrasting hydrologic response to warm season thunderstorms in the urban watershed, White Marsh Run at the top, and in the forested reference watershed, Baseman Run in the bottom. The forested reference watershed sees two pulses of rain rates exceeding 100 millimeters per hour, rain rates shown as a time series through red dotted lines, and we see a dramatic difference in the hydrologic response, both in terms of runoff volume, with the forest reference watershed only having a fraction of the total rainfall appearing as runoff, and in the urban watershed we see something more than 40% of rainfall appearing as runoff at the out of the catchment. Almost 2 orders of magnitude difference in the peak discharge between the two, and these are the kinds of changes that we associate with the alterations of hydrologic response associated with urbanization. Now again, I'm going to focus on Dead Run and Moore's Run throughout this talk, and I want to begin with an examination of extreme floods and make the observation that looking at the eastern United States, and in particular the Mid-Atlantic region, some of the largest flood peaks we've seen at small drainage areas are fairly common floods from urban watersheds, like Dead Run in July of 2004, Moore's Run, multiple events in 2003, 2004, 2005, and 6. So looking at the envelope curve of flood peaks in this portion of the world, these urban watersheds produce a number of events that fit right on the envelope curve of flood peaks. Moore's Run being a particularly interesting one, it has the highest frequency of extreme floods in the conterminous United States. A claim that I make after posing a challenge to John Costa at the Geological Survey. Could he find a USGS stream gauging station that has a higher frequency of flood peaks exceeding 100 cubic feet per second per square mile in unit discharge? In many forested watersheds, a unit discharge of 100 CFS per square mile has a return interval of tens to 100 years. In Moore's Run, 100 CFS per square mile flood peak has a return interval of about 1 month. And this figure is showing observations during the principal BES observing period up to 2004. June 13th, 2003, a unit discharge of 2,000 cubic feet per second per square mile is a flood of record, followed several weeks later by a flood peak on July 6, 2003, exceeding 1,000 CFS per square mile. If we look at how Moore's Run behaves, we see here the red line is the time series of basin average rain rate for this 1,200 CFS per square mile flood peak on July 7th, 2003. The black line is the discharge from Moore's Run. The blue line is discharge from a small tributary basin. There's some characteristic features of response in Moore's Run that are somewhat peculiar. One is that we're not producing extreme floods here by having very large runoff ratios. In fact, the runoff ratio in Moore's Run is often comparable or less than the impervious fraction of the watershed. The response time is extremely fast, and effectively what you get for pulses of extreme rain rates is an unattenuated version of the rainfall rate, or something very close to that. Looking here at the time series of rain rate in red, and the time series of discharge of Moore's Run at a little under 10 square kilometer drainage area in black. Now, it's not hard to explain some of the key details of that. Here looking at representations of the Dead Run drainage network in the late 19th century versus 1935, Dead Run is the quintessential pre-stormwater management urban watershed in which headwater basins have been buried in a storm drain network designed to move water as quickly as possible out the watershed. We have a channel in the lower half of the drainage basin, a single channel, and then a storm drain network that has straightened out the drainage network and moves water as quickly as possible through the watershed. So these are some of the key elements of response, this alteration tied to the storm drain network associated with extreme flood response. One of the characteristics of this alteration is that warm season thunderstorms become the key flood-producing agents. This showing radar reflectivity images for the storm that produced the flood of record, this 2,000 CFS per square mile flood peak in Moore's Run on June 13th of 2003. This just showing 3 radar images from 2347 UTC on June 13th to 0002 UTC roughly 15 minutes later. What we see is a multi-cell thunderstorm system. The yellow color scales here, reflectivity values greater than 45 dBz, indicating heavy rainfall rates. A multi-cell thunderstorm system, this line of heavy rainfall is made up of multiple cells that evolve over the course of the life cycle of the storm system. The life cycle turns out to be quite important. So we have a 15-minute period of this storm system moving over Moore's Run. One of the important observations now, looking at this storm, and we're going to look at it next from a vertical perspective, and we're going to look at the single convective cell that passes over Moore's Run in the northeast corner of the Baltimore City watershed. And again here, the yellow lines give you the demarcation of the Baltimore City watershed. For this flood of record, this 2,000 CFS per square mile flood peak, it's a 15-minute period of rain rates on the order of 200 millimeters per hour that are associated with a collapsing thunderstorm cell. So here, for the same 4 time periods, we see a vertical slice of reflectivity through the cell. We see reflectivity values in the gray in the first image at 2347 that are reflectivity values greater than 60 dBz, 8 kilometers above the ground. That area of hail aloft collapses as the storm cell collapses, producing extreme rain rates over the Moores Run watershed. The 2 principal points here are that this flood is produced by a thunderstorm, a collapsing thunderstorm, and this element of thunderstorm behavior is important in flood response. And then the second question or issue becomes, is there anything about the urban environment that plays into the way this particular thunderstorm and group of cells behaved? And that turns out to be an important problem in looking at the alteration of flood hazards in urban environments. And it's one that we'll come back to. Now, another observation about thunderstorms or systems that produce flash floods in Baltimore is that they have a characteristic life cycle. And that life cycle includes initiation of thunderstorms over the Blue Ridge. So here we have a topographic map showing the central Appalachian region. We have the Chesapeake Bay, the Potomac River shown in blue, the Washington, D.C. metropolitan area, and the Baltimore metropolitan area outlined in black. The color scale showing cloud-to-ground lightning strikes from initiation over the Blue Ridge. The color scale just time. The thunderstorm, in this case, initiated over the Blue Ridge, propagated over the Piedmont, and then interacted with the urban environment and the land-water boundary of Chesapeake Bay. And this is a characteristic feature of thunderstorm systems that produce flash floods in the Baltimore metropolitan area. And by a variety of measures, we can see that the climatology of flash flooding in the Baltimore metropolitan region is largely driven by the climatology of thunderstorm rainfall. And so here, looking at thunderstorms is represented by lightning, just one measure of the diurnal cycle. And so we have the diurnal cycle in the bottom of the occurrence of flood peaks, and we see this pronounced maximum, late evening maximum, that's associated with the maximum in cloud-to-ground lightning frequency over the Baltimore metropolitan region. And there are a variety of ways, looking from seasonal to diurnal, of representing this connection between the climatology of flash flooding and the climatology of thunderstorms. Another way, a spatial perspective, is looking at thunderstorm frequency here through cloud-to-ground lightning strike, flash density. This is warm season, June, July, August climatology, 1991 through 2005. Warm season cloud-to-ground flash density and strikes per square kilometer per year. We see a pronounced minimum over the interior of the Appalachian Mountain region and the Valley and Ridge, a maximum just east of the Blue Ridge. We see Chesapeake Bay, a maximum just to the west of Chesapeake Bay, and very sharp gradients over the Baltimore and Washington metropolitan regions. So this interplay of terrain to the west, land-water boundaries to the east, and the urban environment is an important element of the way thunderstorm systems behave in this particular region. So in examining the flood response, one of the key tools that we've used in the Baltimore metropolitan region in the Baltimore ecosystem study is studies of extreme floods through surveyed high water marks to examine the hydraulic and geomorphic impacts. So for this flood of record in Moores Run in June of 2003, days were spent surveying high water mark or identifying high water marks, and then weeks spent surveying high water marks, producing what's shown in the upper left-hand figure here for the Moores Run watershed is a very detailed map of high water marks for the valley bottom of Moores Run. We use these observations along with two-dimensional depth average hydraulic models to examine the alterations of flood response and open channel response associated with the way altered flood hydrology has changed the channel floodplain system. So important observations are that watersheds like Moore's Run, in which we've dramatically increased the frequency of large flood peaks, we have dramatic changes to the channel system itself. We have a high-velocity environment in which we have very, very dramatic incision and widening of the channels. The other observation is that constriction expansion reaches play a very important role in both floodway propagation and in alteration of channel valley bottom properties. Here, Radicke Avenue and Sinclair Avenue being the two principal crossings of Moore's Run. In the upper right-hand figure, we show hydraulic analyses at peak discharge for the reach below Sinclair Avenue, the constriction and expansion associated with the bridge abutment, and then a natural constriction and expansion and the reach below play into very dramatic alterations to the floodway propagation. So attenuation of floodways in the Moore's Run channel are largely associated with these constriction expansion reaches associated with urban infrastructure. Important elements looking throughout the Baltimore metropolitan region in terms of how urbanization alters flood response. So in Moore's Run, what we have is we have a channel that is dramatically incised and widened. The figure on the lower right-hand, or in the lower left-hand portion of this image, you can actually see an incision of the channel that has uncovered a sanitary sewer. So channels that are much wider and much deeper than is typical of 10 square kilometer watersheds, even in much of the Baltimore metropolitan area. This alteration of the channel geometry and valley bottom geometry plays an important role both in the floodway propagation, but also in terms of the flood hazards that are associated with extreme floods in these regions. So Moore's Run is an example of some of the most profound changes that take place in urban watersheds. They're changes that are associated with the way urban watersheds evolved prior to stormwater management associated with the Clean Water Act. And throughout the Baltimore metropolitan region, we have watersheds that look to some degree like Moore's Run. The broad story, though, in looking at urban watersheds in Baltimore, as in other portions of the eastern United States, is that we have a more heterogeneous mix of development. And we'll examine that now through studies that have been carried out in Dead Run. The image here of Dead Run, 14.3 square kilometer drainage basin at the USGS stream gauging station at Franklintown. Over the last 5 years, we've gauged 5 tributary watersheds denoted DR1, DR2, DR3, DR4, and DR5 to examine the heterogeneities of response in the Dead Run watershed and compare it with the heterogeneities in response that we see throughout the Baltimore metropolitan region, and in particular looking at the principal study watershed of the Baltimore ecosystem study, the Glens Falls watershed. And so to put the Dead Run watershed in, to put the Dead Run watershed in perspective of Glens Falls, it's located along the southwestern margin of Glens Falls, right on the western margin of Baltimore City. It is a watershed that's been developed over the last 200 years. The name Dead Run comes from a colonial area cemetery that's located in the watershed. So development in Dead Run has a very long history that extends to the present with significant portions of the watershed, particularly in the northern DR1, DR2 sub-watersheds that were carried out post-Clean Water Act over the last 20 years. By contrast, looking in the upper Glens Falls, the Glens Falls watershed at Delight, it is characteristic of post-Clean Water Act, post-storm watershed management. The red colors here show regions of stormwater detention facilities, the locations of stormwater detention facilities. The grayscale in each of the subwatersheds indicates impervious surfaces. The message in the Upper Gwynns Falls is that with stormwater management, effectively all of the impervious surfaces that are created or associated with stormwater management facilities, and it has a dramatic impact on hydrologic response of watersheds. One of the reasons that Dead Run is particularly interesting is that it reflects this mix from the Upper Gwynns Falls with post-stormwater management development to the types of response that we see in Moore's Run. To give an example, just a characterization of the seasonal mean runoff over the Gwynns Falls watershed. The blue line here shows mean runoff of Gwynns Falls at the 120 square kilometer outlet of the drainage basin. What we see is that we have almost a factor or more than a factor of 2 increase in runoff from Dead Run to the upper portion of Gwynns Falls. So we have pronounced heterogeneities in response that are associated with principally stormwater management. And looking at the difference in runoff between the Upper Gwynns Falls and Dead Run, really the key element is the storm event difference. So in magnitudes of runoff, Dead Run has larger runoff solely because of increased runoff production from storm events. So the Moore's Run mode of development for the watershed. Now, even looking within the Dead Run watershed itself, we do find the same range of heterogeneity in response. The upper left-hand figure here showing, again, this partitioning between impervious and pervious portions of the watershed, with the grayscale indicating impervious portions of the watershed, and the lighter colors indicating pervious portions of the watershed with some form of urban soils. The bottom left figure shows representations of rainfall from a storm event perspective, and then storm event runoff between DR1 and DR2, which are 2 watersheds located in the northwest portion of Dead Run. DR2 residential, DR1 is industrial watershed. So contrasting response in Dead Run at scales of approximately 1 square kilometer are associated with this heterogeneity and development of the watershed. So this is the type of heterogeneity that we see within Dead Run and within the broader Baltimore metropolitan region in terms of runoff production and hydrologic response. We also look at the Dead Run watershed here through the drainage network, with the blue lines indicating surface channels and the orange lines indicating the main elements of the storm drain system. And so the principal alteration that's taken place in Dead Run is associated with the amplification of drainage associated with the storm drain network. One of the interesting features of Dead Run is looking at 14.3 square kilometer scale of the USGS stream gauging station at the outlet. Even with the heterogeneities and runoff production, what we find is that we get a unit pulse of large rainfall over the watershed. The response at the outlet looks quite similar. And this translates directly into elements tied to the storm drain density and the distribution of drainage over the watershed, and effectively the uniform distribution of travel times within the watershed, and the difficulty of altering travel times substantially. So this unit response in the presence of pronounced heterogeneities is again one of the important features of the Dead Run watershed. The Dead Run during the DES observing period has also seen extreme floods. In fact, the flood of record over the past 50 years occurred on July 7th, 2004. The upper right-hand figure shows this same type of activity where days of flagging high water marks and then weeks of surveying high water marks provides the capability of characterizing the inundation extent at peak discharge for the July 7th, 2004 event. For this particular event, in the bottom figure, we show time series of basin average rain rate derived from the hydronetrad rainfall analyses that you'll hear about in the next Cyberseminar, and then discharge at the outlet of Dead Run at 14.3 square kilometers. So in contrast to the Moores Run flood peak in June of 2003, what we have is rainfall accumulations at a 1 to 2 hour time period that have very, very long return intervals. The figure in the upper left-hand corner is, again, the hydronetrad combined with rain gauge analysis of storm total rainfall, where we see this sharp maximum over the western margin of Baltimore, and in particular over the Dead Run watershed, which is outlined in the image. So 125 millimeters in a 2 hour time period over Dead Run is responsible for the largest flood peak in Dead Run over the past 50 years. The types of analyses that are carried out with high water marks are illustrated here. So again, the high water marks in the upper right-hand corner are a network of stream gauges showing discharge time series with the Franklintown U.S. Geological Survey stream gauging station being the most downstream, two stream gauging stations at drainage areas of approximately 4 square kilometers that are shown, or the areas of those are shown as the tributaries in the upper portion of these figures. Hydraulic model analyses allow us to pin down peak discharges throughout the watershed, and through these types of analyses and the analyses of rainfall, we're able to examine how the spatial and temporal distribution of rainfall translates into the magnitudes of flood peaks over varying basin scales throughout the Dead Run watershed. So the most one of the striking features that Peter Nelson has examined about the Dead Run channel network is that, in contrast to other studies that have been carried out in the Piedmont, the Dead Run channel has been remarkably stable over a long period of time. And the figure in the upper left-hand corner of the image shows Peter's analyses of the Dead Run channel over a 100-year period, illustrating the stability where the only changes that have taken place have been associated with anthropogenic alterations of the channel system itself. Peter's carried out some fascinating work, again using these detailed hydraulic models constrained by high water marks to show that much of the stability of the Dead Run channel is tied to geologic controls of flood peak magnitudes in areas of the watershed. The images on the bottom left-hand portion of this image show Peter's analyses of peak discharge in the meander bend shown in the upper left image. Analyses of the geologic structure of the valley bottom show that the high stream powers and shear stresses occur in geologically controlled portions of the watershed. The big message is that unlike Moores Run, what we have in Dead Run is a channel floodplain system that has shown remarkable stability over extended periods of time. And there's been channel widening and incision in some locations, but the principal theme here has been pronounced stability over extended periods of time. So looking at the storm that produced this record flood in Dead Run in July of 2004, two analyses here illustrate aggregate storm properties. Again, in the upper right-hand corner, the hydronetrad rainfall analysis showing the 125 millimeter maximum 2 hour time period with a bullseye over Dead Run in the northwest corner of Baltimore City. Cloud-to-ground lightning observation showing similar features with some interesting departures from the rainfall analyses. Both rainfall and lightning essentially drapes around the metropolitan regions of the Washington, D.C. metropolitan area and the Baltimore metropolitan region. One of the questions this raises is whether the urban environments, in fact, have an important role in the evolution of the thunderstorm system that produced heavy rainfall over this region. And so how are the flood hazards associated with warm season rainfall tied to these urban alterations of thunderstorm systems? And so we'll examine that through the observations that are available, like the Moores Run flood in June of 2003, and like essentially all of the major flood peaks in urban watersheds in Baltimore, the same life cycle of initiation of thunderstorms on the Blue Ridge, propagation over the Piedmont, and then interaction with the land-water boundaries, Chesapeake Bay, and Baltimore-Washington metropolitan region to the west. The 2004 storm that produced record flooding in Dead Run was also the record cloud-to-ground lightning producer in the Baltimore metropolitan area. Again, here the color codes highlighting timing of the lightning over the region. So severe thunderstorms shown here from 1845 UTC to 2115 UTC. The period of heaviest rainfall over the Dead Run watershed. Here, radar reflectivity observations, also showing each of the cloud-to-ground lightning strikes. And what we see is, in the early portion of the storms, a series of multi-cell thunderstorms passing south to north over the Dead Run watershed, ultimately organizing into a line of thunderstorms that passes over the region and dissipates as it approaches the Chesapeake Bay region. So one picture of the evolution, and then looking more closely at individual thunderstorm cells, repeatedly what happens as cells pass over the Baltimore metropolitan region. And here, storm tracking analyses of a series of cells that pass over the region is that the cells either angle to the west of the Baltimore metropolitan region, or they remain stable in the southwest corner of the Baltimore metropolitan region, again suggesting that the urban environment may in fact play an important role in the way the thunderstorm system evolves and in controlling the distribution of extreme rainfall rates from the storm. So in looking at the urban impacts on thunderstorms, the typical elements that are examined, urban heat island is certainly one of the players. The thermal contrast between the urban core and the surrounding forested landscapes and agricultural landscapes can play an important role in some settings. The urban canopy effects in which we alter the roughness of the atmospheric boundary layer, also a candidate. And then the final potential player are urban aerosols and their alteration of cloud microphysics. For the July 2007 storm, we have observations from a LIDAR at UMBC, a vertically pointing LIDAR, and then disdrometer observations of raindrop size distributions, which are shown at the bottom. And looking at aerosol impacts on precipitation, the principal impacts that have been examined deal with increased cloud condensation nuclei and suppression of precipitation, the presence of giant aerosols that can enhance precipitation, and hygroscopic growth in which we have aerosols that grow at relative humidities larger than 100% and potentially enhance the development of extreme precipitation. From the LIDAR observations, one of the things that can be inferred is that hygroscopic growth is in fact an important element. Anomalous drop size distributions for the July 2004 event suggest this link between aerosol processes may have in fact been an important element. But this is a difficult one to look at and one that needs much closer examination. So observational studies from surface observing systems, from remote sensing systems, provide us capabilities of looking at how the storm systems that produce extreme floods in urban environments behave. Ultimately, though, what we need to be able to do is integrate these observations into modeling analyses in which we examine specific processes to sort out their impact on the distribution of rainfall associated with these flood-producing thunderstorm systems. To do this, Alex Delekos has carried out a series of simulations using the Weather Research and Forecasting model. The figure here shows the two domains that he used for simulations, an inner domain that includes the Valley and Ridge portion and Piedmont portion of Virginia and Maryland, the Baltimore-Washington metropolitan region, and then the Chesapeake Bay region in the southeast corner of the watershed. So Alex has carried out a series of simulation studies to examine the July 7, 2004 storm. And to carry out the simulations, the first step is to show that, in fact, we're able to do a reasonable job in simulating the rainfall with the model. And the figure here, the upper one shows HydroNexRad storm total rainfall analyses. The bottom figure shows the Weather Research and Forecasting model storm total for the base simulation in which we account for urban impacts as well as the impacts of Chesapeake Bay. So in a series of numerical experiments, what Alex has been able to show is this initiation of the thunderstorms in the Blue Ridge has a very particular element associated with it, at least for the July 7th storm, and that is a convergence-induced spin-up of a mesolow at the Blue Ridge, which plays an important role in the subsequent storm development. So using model simulations, Alex is able to identify mechanisms by which terrain plays an important role in initiation here. Alex is also able to show that the Chesapeake Bay plays a fundamental role as a thermal boundary in controlling the evolution of the storm system, and in particular, impending heavy rainfall along the western margin of Chesapeake Bay. Alex is also able to show that the urban canopy effect has a very important control on the distribution of low-level convergence and divergence. That in turn plays an important role in evolution of storm elements, tying into these analyses showing individual storm cells propagating to the west of the Baltimore metropolitan area or remaining stationary on the south side of the Baltimore metropolitan area. It's also straightforward to show that in this particular case, there's certainly no urban heat island effect, and that's tied to very strong winds associated, southerly flow associated with event. So combining observations with model analysis has provided an important way of examining the hydrology, the hydraulics, and the hydrometeorology of extreme flooding in the Baltimore metropolitan region. It's certainly critical to have the observations to constrain the model analyses, and the two together provide the best way of moving forward in improving the understanding of flood hazards in urban environments. Now, just an examination of one of the analyses, the types of numerical experiments that Alex carried out. In the upper figure, we show a control run and then a no Chesapeake Bay run in which Chesapeake Bay is converted from a water boundary with thermal properties tied to the free water surface to one in which we literally, we don't pave the bay, but we turn it into agricultural land. So it has profound impacts on the thermal evolution of the storm region. And then looking at the rainfall distribution, the bay versus no bay simulations, the effect of having a realistic representation of Chesapeake Bay is to constrain heavy rainfall to the western margin. The no bay simulations move the heavy rainfall over the bay and into the eastern margin of Chesapeake Bay. So these are the types of simulation studies that provide context by which we can interpret the types of observations that have been an important hallmark of the Baltimore ecosystem study and will continue to be an important hallmark over the coming years. So in summarizing, I'd like to emphasize from the bottom up that one of the key problems that we need to be able to address is the variation of flood hazards over urban regions. So we have pronounced heterogeneities in hydrologic response. We have pronounced heterogeneities in the hydraulics that are associated with anthropogenic alterations of the channel floodplain system. And we also have potentially pronounced alterations of the storm systems themselves. Characterizing the variability of flood hazards over an urban region is going to be a very difficult problem, both for applications that are tied to assessing flood hazards for problems like flood insurance specification, but also for problems that deal with forecasting of flood hazards and flash flood forecasting. It translates into a very, very difficult problem of assessing the impact of the urban environment on the evolution of warm system thunderstorms. This is an area in which looking at the urban heat island effect, looking at the urban canopy effect, and looking at urban aerosols can all potentially translate into pronounced alterations of flood hazards. And so in looking at the Baltimore metropolitan region, what we see is that flood peak magnitudes in urban watersheds are comparable to the largest we see throughout the eastern United States and the mid-Atlantic region. We see that our climatology of urban flooding is directly linked to the climatology of warm season thunderstorms, and we need to view the two in that context. And looking at the climatology of warm season thunderstorms, this characteristic life cycle in which complex terrain to the west and land water boundaries to the east and the potential for urban impacts all play into the way these thunderstorm systems evolve. And then finally, in examining heterogeneity in response both from the hydrologic perspective and from the perspective of alteration of the channel floodplain system in a rapidly altering environment produces tremendous challenge for examining urban flood hazards. So thank you very much, and I would be happy to attempt to answer any questions that you have.
Ladies and gentlemen, if you wish to ask a question, please press star followed by 1 on your touch-tone telephone. If your question has been answered or you wish to withdraw your question, press star 2. Please press star 1 to begin.
Or you could also type a question into your chat box, and we'll relay that question. Jim will probably see it also if you address that to all participants.
So a question, how do urban planners use these simulation tools to better manage stormwater? One of the observations that I would make here is that, particularly in Baltimore County, the managers in Baltimore County are very innovative in approaching problems of stormwater management. They're very interested in attempting to use stormwater management both to improve problems related to flood hazards, but also there's the paired issue that I didn't discuss today, and that is these alterations to the channel floodplain system also have big impacts on the water quality. The key element is that the planners in the Baltimore metropolitan region are very open to the input of the scientific community, and that's been facilitated directly through the Baltimore Ecosystem Study. Let's see if I...
Are there any questions out there?
And sir, you have no audio questions at this time.
There's one in the chat box, Jim. Do you see that one from?
Yeah, so bridges are essentially unintended detention structures. So what role do these structures have on floods and on water quality? And how can this more effectively be planned? The problem is that bridges and bridge abutments do in fact have a very profound impact on flood inundation, and an important component of the problem is that For the very large floods, most of the attenuation in flood peaks is going to be associated with storage from these constrictions in the valley bottom. And this role as a storage element has impacts on the downstream incision and widening of channels like in Moore's Run, and these are certainly unintended consequences. They're detention structures that are used very infrequently in most places, so they really don't serve the kinds of functions that natural stormwater detention structures serve for each storm event. They're very much extreme events detention structures that have a kind of a wide range of surprising consequences, and I think attempting to use them as any sort of a design structure would be exceedingly difficult, and avoiding the detention effect of bridges and bridge abutments is in fact something to look for in urban development. Steve Birch has asked the possibilities of more distributed infiltration and the headwaters, possibilities of roof gardens. A very interesting question. One of the graduate students at Princeton working on the problem, Kate Meyerdirks, is examining precisely that issue using hydrologic and hydraulic modeling studies. The question is, what impact can you have with basin-wide policies that deal with altering infiltration through policy, whether it's porous pavement, roof gardens, or what have you. And the basic question that needs to be answered is whether you can really have any impact at all. And the jury's certainly out on that. One of the observations I would make here is that we've really been surprised at urban soils. Urban soils are obviously very, very structured soils. In many cases, they're soils designed to have specific hydraulic properties. They're supposed to, in most cases, be highly permeable for a very thin surface layer, but typically very impermeable at a very shallow layer. And so one of the really big challenges in looking at the runoff production side of urban watersheds is sorting out how urban soils behave. And I think that's as big a portion of the problem as attempting to then look at constructed elements of altered infiltration. Yeah, Andy Miller makes the observation about embankments that block flow, which is an important point. Let's see. The question from Vitek Krajewski, the current level of skill in forecasting these floods. That's it's a very interesting question. We've had very close and good interactions with the Weather Service Forecast Office in Washington, D.C., and particularly the Science and Operations Officer, Steve Zubrick, there. And he's been very interested in learning about the sort of details of how these urban watersheds work. Very interested in understanding the difference between a Moore's Run type watershed that responds very, very quickly, has very incised channels, and consequently different flood hazards than natural channels, versus watersheds in the Upper Gwynns Falls with extensive stormwater management. What it's translated to is what I think is a very sophisticated approach to flash flood warning from the forecast office in Washington, D.C. Having, again, this information transfer from the Baltimore Ecosystem Study to the implementation agency, in this case the National Weather Service Forecast Office, is an important element of taking the types of studies that we're carrying out and translating them into practice. Let's see. Simulations, the interface with urban policy on green roofs. So can the simulations be interfaced with urban policy on green roofs? Very good question, and it is again one of the things that that Kate Meyerders is directly examining. And from the modeling perspective, she's able to do that. The key element is convincing ourselves and then convincing the managers, convincing the scientific community that the models capture the key elements of hydrologic response in the watershed, and then looking at our model alteration and the changes in response in the modeling, then we'll have confidence that that our model results, in fact, reflect what will happen. Let's see. Okay, Claire Welty, another very important point, as part of the Baltimore ecosystem study, an intensive effort at developing groundwater models for the region, with one of the focus areas being the Dead Run watershed, designed specifically to examine this question of how infiltration varies across the urban environment, and then ultimately being able to translate that into the kinds of questions that Amelia's raising about how does that translate then into urban development considerations. Okay, other questions? Did I miss any?
Well, I think you got all there in the chat box. Are there any questions on the telephone line?
And you have no questions at this time, sir.
Okay, thank you.
So Jerry Stenger asked the question, what is an urban soil? And I'll answer that with an anecdote. In Dead Run, we had been carrying out permeameter studies of saturated hydraulic conductivity in a variety of settings, and we worked in a particular site. It was a high school area that abutted one of our stream channels. It was a valley bottom, and a stormwater detention pond was being constructed on the site. And one day I went up to one of the engineers at the site, and I sort of described, you know, we're surprised at what happens here. You know, we take these permeameter measurements, and we get really high surface hydraulic conductivities, and then there's this impermeable layer about 50 centimeters, and you know, really striking contrast in the soil properties. And the guy looked at me like I was a dump, and his response was, "That's the way we built them." And so one answer to Jerry's question of what are urban soils is that quite often they are constructed soils, and they're soils that are constructed to serve particular construction purposes in the urban environment, and even beyond the buildings and roads per se, the soils that we typically see have properties that are largely not those that are associated with long soil formation processes, but with the way a contractor has actually set up the soils. Okay, so certainly constructed soils, permeameters are extremely limited devices. Yet we've certainly learned that attempting to make extensive measurements with those. And I think the point I shouldn't leave is that there is a very homogeneous characteristic to urban soils, and as Steve alludes to, there's tremendous variability in urban soils. Let's see, Su Liang The range of the groundwater table in the region with urban cover. Now, that's a really interesting question, and we don't know the answer. As Andy Miller responded, Claire Welty has a very extensive program to look at urban groundwater, and we really have no clue as to the details of how urban infrastructure alters the regional groundwater table. Good question. Okay, any other questions?
Well, I think if there's no more questions at this point, during the chat, some of you may have noticed that, or the presentation, that in the chat box I posted a link to the PDF version of Jim's presentation. If you didn't catch that link, you just can go to quasi.org/sem-current.html, or it's on the navigation bar, and then scroll down to where Jim's presentation is listed, and there's a link there to the PDF version. I want to thank everybody for participating. This was a very nice crowd. I want to especially thank Jim for taking the time out to put together this presentation. It was extremely interesting, and then taking the time out to present it today and answer our questions. Again, there's a couple upcoming events that I have highlighted on the screen here. If you just visit the quasi.org website, there's more things happening throughout the country, not just involving Quasi, but the hydrologic community in general. Again, if there's no more questions, I think we can wrap it up for today. Look probably next week for actually a link to the recorded version of this presentation so we can relive the moment. Jim, thanks very much, and that's it for us. Thanks.